Good afternoon. Welcome to this KCI webinar on stream restoration crediting. My name is Mehmet Bose. I'm a vice president with KCI Technologies, and I'll be today's moderator. Today's topic will provide a brief background on TMDLs and MS4 permits in the context of stream restoration. Presenters will discuss how to compute nutrient and sediment load reduction credits. Our presenters today are Shannon Lucas and Hannah Scholes. Shannon is a senior PM with 18 years of engineering experience at our headquarters in Sparks, Maryland. Hannah is a design engineer with KCI, again at our Sparks, Maryland office. With that, I'll turn it over to Shannon.
Thank you so much, Mehmet. So today we're going to start with a brief overview of TMDL and MS4 permits as regulatory drivers for stream restoration. Then we're going to look at the regional Chesapeake Bay TMDL as an example and dive into the nitty-gritty of the latest Chesapeake Bay expert panel protocols and the MDE impervious acre crediting guidance. We've seen a lot of recent changes that can have significant impacts on how stream projects are credited toward the Bay TMDL. So why stream restoration? This could be a week-long topic. I'm going to do a 30-second slide on it. The way we use our land can cause stream instabilities. Agricultural practices such as clearing forest and channelization can lead to channel instability. Also, development alters hydrology by introducing storm drain networks and impervious surfaces. Impervious surfaces include areas that impede water from infiltrating into the ground. So rooftops, roads, sidewalks, etc. So these destabilize channels, which can lead to excessive erosion. And channel erosion contributes significant amount of excess sediment and nutrients. Restorations performed for various reasons, including to mitigate for unavoidable impacts, to protect infrastructure and property, to improve water quality and habitat, and to provide resiliency by restoring natural floodplain and wetland functions, which store flood flows and carbon. So let's talk briefly about the regulatory drivers and define some acronyms. The Federal Clean Water Act was established in 1972 and requires that states identify and report impairments to rivers. This is also called the 303D list. Impairments can be things like pathogens, nutrients, metals, PCBs. The EPA defines the total maximum daily load, or TMDL, as the maximum amount of a pollutant allowed to enter a water body so that the water body will meet and continue to meet water quality standards for that particular pollutant. A TMDL determines a pollutant reduction target and allocates load reductions necessary to the source of that pollutant. So in essence, it's a pollution diet for streams and water bodies. Some more big acronyms: the National Pollutant Discharge Elimination System, or NPDES permit, helps address water pollution by regulating point sources that discharge pollutants to waters of the US. The Municipal Separate Storm Sewer System, or MS4 permit, aims to reduce pollution from runoff, which flows through storm drain systems to local streams, ponds, and waterways. The MS4 permit includes elements like illicit discharge detection and elimination, public outreach and education, reduction of pollution from runoff, and making progress toward meeting your local and regional TMDLs. In summary, the Clean Water Act takes a water quality approach to protecting our waterways. TMDLs define the stream impairments and quantify necessary load reductions to meet a stream's designated use. And MS4 permits regulate the stormwater sector to reduce or eliminate pollution. So we're going to be talking about the Chesapeake Bay TMDL and how the protocol methodology was developed through the Chesapeake Bay program and has been recently updated to quantify nutrient and sediment load reductions. So for those of you who are not familiar with the Chesapeake Bay TMDL, it was established in late 2010 officially, and it put the Chesapeake Bay on a pollution diet to reduce its excess nutrients and sediment. The load reductions required to meet the Bay TMDL were allocated to each state within the Chesapeake Bay watershed, and then further allocated by the states to their local municipalities, and then also divided into separate sectors. This problem is not unique to the Chesapeake Bay. In fact, the EPA reports that nationally 46% of rivers and streams have excess nutrients. The goal is in the Chesapeake Bay to have the TMDLs addressed and the bay cleaned up by 2025. So now we're going to talk about how stream restoration can generate credits toward the Bay TMDL. In 2014, the Urban Stream Restoration Expert Panel protocols were completed. So a big shout out to all the experts out there that participated and volunteered and dedicated their time and energy to putting these together and really taking these complex systems and topics and putting them into usable protocols. Now that they've just had recent updates to these protocols, there are 5 ways that you can generate credit for stream restoration. Protocol 1 is the most widely applied protocol. It's the Prevented Sediment Protocol, and credits first through third order perennial streams that stabilize banks and prevent sediment erosion in actively degrading channels. The Hyporeic Exchange Protocol 2 credits projects that include design features to promote denitrification during base flow. Protocol 3 is a floodplain reconnection protocol, which provides credit for projects that reconnect the stream channel with its natural floodplain. Protocol 4, which we're not going to talk about much today, is the Dry Channel Regenerative Stormwater Conveyance Protocol. This is for zero water channels with intermittent flow and is credited as a stormwater retrofit practice. And Protocol 5 is the newest protocol, the Outfall and Gully Restoration Protocol. So we're going to review the basic steps for protocols 1, 2, and 5 and identify some of the key changes in the guidance and updates for the protocols, including Protocol 3. To be eligible for credit, the restoration has to be for an actively degrading channel, restore more than 100 linear feet. It has to provide a comprehensive restoration and functional uplift. So you can't get credit if you are just out there patching up a local bank or stabilizing an exposed utility crossing or something like that. It has to have a more systemic approach to the restoration. The new guidance does identify limitations to armoring, which Hannah's going to talk about in more detail. The protocols are additive, so you can generate credit for protocols 1 or 5, and then those are added to credits that are generated through protocols 2 and 3. To get credit, you do have to do post-construction monitoring, maintenance, and verification. So while we're going to get into a good bit of detail with the computations, we do encourage you all to read the guidance documents that are found at this link above, and they go into significantly more detail. They also provide the research and basis behind the guidelines. So without further ado, I'm going to pass things off to Hannah to get into the details.
So I'm going to start to talk a little bit more about protocols 1 and 2, but first just wanted to say that the revised guidance takes effect on July 1st, 2021. And some of the main changes, which we'll go into more detail on, are the new designation of armoring practices. There's sampling requirements for bulk density and nutrient concentrations. And then there's no longer an application of delivery factors as a part of the protocols. Before going into the specifics of Protocol 1, it's important to mention the new designation of armoring practices. So rock used to stabilize infrastructure, such as retaining walls, are not creditable, and boulder or rock toe protection is allowable with full credit on up to 30% of the total restored banks, so the combined length of the right and left. Any bank length that's armored by a practice designated as creditable with limits that exceeds the 30% limit will be proportionally subtracted out from the final pollutant load reductions. And I'll show an example on the following slide, and hopefully it'll make a little bit more sense. but the 30% stems from the estimated percentage of the total length of stream banks of a project that would represent the outside bend of pools. So here's an example of a situation of a creditable with limits project. The total length in this situation is 1,000 linear feet, so 500 feet of left bank restoration and 500 feet of right bank restoration. The total armored length is 400 linear feet, which is 40% of the total length. So that's 10% over the 30% limit. So the calculated reductions from the protocol calculations would need to be reduced by 10%. So now I'm going to transition to talking more about Protocol 1, the steps behind it, the required computations, and then follow up with an example. So the first step to Protocol 1 is to estimate the stream sediment erosion rates and annual sediment loadings. This step involves fieldwork and an analysis of the erodibility of stream banks. The second step is to convert the erosion rates to nitrogen and phosphorus loadings, which also requires fieldwork for sample collection and laboratory analysis. The third step is then to estimate the reduction attributed to the restoration. So the main method for estimating stream bank erosion potential is through the Banks method, the bank assessment for non-point source consequences of sediment. The main goal of Banks is to determine a stream bank's erosion rate, or really how much are the stream banks of a particular project eroding each year. There are two components to the Banks method, the first being BHI, so the Bank Erosion Hazard Index. BHI is a method for estimating stream bank erosion potential based on different physical characteristics such as bank height, root depth, root density, and all of those characteristics need to be measured in the field. The field measurements are converted to numerical scores, which I'm really not going to get into detail on because Rosgin's 2001 paper really explains how that data is used. But in the end, the numerical score is used to determine a narrative rating for each individual bank segment, and then those range from very low to extreme erosion potential. The second step to the Banks method is NBS, or near bank shear stress. There are 7 alternatives to measuring NBS at a particular bank. They range from completing a rapid visual assessment based primarily on the location of depositional features or a channel's plan form, all the way to measuring a velocity gradient. So the methods primarily used are methods 2 or 5, and they involve either estimating the radius of curvature or maximum near bank depth along with the bank full width. So the results are an estimate of the local shear stress along the bank. Ultimately, BHI is the assessment of a bank's susceptibility to erode, and NBS is the assessment of the force exerted onto the bank. So it's also important to remember photo documentation for BHI assessments. It's especially helpful to include a survey rod in the photo. It helps really add scale. And it's really helpful if you ever need to go back and reference any of your banks. The link shown here is for the bank spreadsheet created by U.S. Fish and Wildlife Service and EPR. So now let's talk about sediment sampling. A major change to the protocols is the requirement for site-specific sediment samples. This is because they really realized that bulk densities, for example, varied greatly, and the numbers used in the previous guidance often overstated the bulk density and resulted in inflated loads. So according to the revised guidance, sampling is required, and sampling needs to be taken at least every 200 to 500 feet. So at each sampling site, a bulk density, nitrogen concentration, and phosphorus concentration sample need to be collected. The samples should be collected on alternating banks. So if your first sample was collected on the left bank, the next sample should be collected on the right, as long as you're sampling from erosional areas. So you shouldn't sample from a depositional feature such as a point bar or any sort of slumped bank material. The samples should represent each soil horizon proportionally. So if there's different soil horizons identified, like in the photo on this slide, you should collect samples from each horizon. The samples should be collected in a manner to result in an undisturbed bank sample. And then there are specific laboratory methodologies for total nitrogen and total phosphorus concentration included in the guidance. So it's important to coordinate with laboratories beforehand to make sure that they actually perform the specified tests. And then in the end, the results of all of the sediment sampling should be averaged. So for an individual project, you will have one bulk density, one nitrogen concentration, and one phosphorus concentration. So the actual methods of sample collection range in degree of effort. So a push soil sampler involves pushing a core sampler into the bank, but really the volume of the sample needs to be determined and the sample shouldn't be disturbed. So using this tool, the sampling diameter and depth that the sample is sampled into the bank is important to note in order to really determine the volume. So an easier method may be using a moisture can or a PVC pipe and using a mallet to really get it into the bank, because in the end, you would end up with a known volume that's in a can or in a PVC pipe, which can easily be secured on either end, capped, and transported. Again, it is important to coordinate with laboratories beforehand, just in case they require a minimum volume or have a specific way that they want the samples to be delivered. So for example, the nitrogen and phosphorus tests may need to be kept over ice before they get to the laboratory. Here's just a picture of a bank that's eroding. A sample was collected in a moisture can, and that resulted in an undisturbed bank sample, so the volume can easily be determined. After the fieldwork for BHI and NBS assessments, along with the fieldwork for sample collection is complete, the next step is to convert the combination of narrative ratings to actual erosion rates. So that's done with erosion rate curves. There are different regional curves developed. So there's one for North Carolina, DC, Wyoming, and Colorado. The one on this slide is the DC curve. So the x-axis represents the different narrative ratings for NBS, and then each regression line represents a different BHI narrative rating. So combining the two will result in a lateral erosion rate on the y-axis. So you can see here on this DC curve, there are some certain combinations that are missing. So a very low NBS combined with a moderate BHI technically is off the regression line. So extrapolation may be required, or you may need to supplement missing erosion rates with data from other curves. And then this link goes into more detail on NBS and BHI assessments, so you'll be provided that link at the end. So this is an example of a bank that was assessed for BHI and NBS. The bank was assessed in the field and the results determined that the BHI rating was high and the NBS was low. So then looking at the erosion curve on the right, a low NBS combined with a high BHI resulted in a lateral erosion rate of 0.4 feet per year. So once the erosion rates for each bank segment have been determined, those rates need to be converted to volumes using the other data collected during the BHI analysis, so the length of each reach and the height of each bank. So multiplying those three values together gets us the volume of bank estimated to erode each year. Once the volume of potential sediment eroding per year is determined, the next question is how much TSS and nutrients are in that volume. So TSS reduction is calculated by using the results of the laboratory analysis for bulk density. And then similarly, the nitrogen and phosphorus reductions are determined by applying the site-specific nutrient concentration. So up till this point, all of the calculations are assuming that a restoration will prevent all potential erosion of existing conditions. So in order to be more conservative, an efficiency is applied, and that's typically 50%, meaning that a restoration will be 50% effective at reducing bank erosion. So the 50% can be refined with long-term post-construction monitoring data, but it does need to be approved by regulators. So now I'm going to transition to an example of Protocol 1. This is a short restoration project in Frederick County, is about 200 linear feet. It qualified for Protocol 1. Focused primarily on the right bank because the left bank was a depositional feature and you don't complete banks assessments on depositional features. So the study bank was split into 3 sections with unique bank features that resulted in moderate or high B-high ratings, primarily because of differences in surface protection and varying bank heights. And all of the study banks resulted in a low NBS. Site-specific sediment sampling was done here, and the average results resulted in a bulk density of 79.7, total nitrogen of 4.32, and total phosphorus of 1.39. So here you can see the different bank reaches and the associated B-high and NBS ratings, which are noted under the column number 1. To go from 1 to 2, the DC erosion rate curve was used to determine a lateral bank erosion rate per bank segment. To go from 2 to 3, the lateral erosion rate was multiplied by the length and height of each bank segment. And then those values were multiplied by the bulk density to result in column 4, or the predicted erosion amount. And those values are all summed together to result in a total volume per year, which is 21.5. Okay, so after we determined the total volume of sediment that was eroding, which was 21.5 tons per year, using the average nutrient concentrations, the total nitrogen and total phosphorus load reductions are determined. So a 50% efficiency is applied. So that's assuming that the proposed restoration will be 50% effective. So in the end, the 3 numbers at the bottom represent the local TMDL pollutant load reductions for this project calculated from Protocol 1. So now I'm going to transition to talking about Protocol 5, or the other prevented sediment protocol. So if a project is an outfall or gully stabilization, really a channel in the headwater transition zone, the qualifying conditions are less strict and allow for limited use of pipe extensions or drop structures as long as they're not introducing new aquatic organism passage issues. So the qualifying conditions for Protocol 5 include showing signs of gully erosion or head cutting. There might be a high existing slope compared to a calculated equilibrium slope. There may be nick points or head cuts greater than 6 inches. Potentially there are slab failures or bank failures, but the project still must use a comprehensive approach for stream restoration design, has to comply with state and federal permitting requirements, and has to meet post-construction stability criteria, as well as have established vegetation. There is no minimum length for Protocol 5. So unlike Protocol 1, you do not need to hit the 100 linear foot minimum. And it's also important to note that if Protocol 5 is applied to a perennial stream, the armoring limitations presented for Protocol 1 are still applicable for the project. So Protocol 5 tries to incorporate vertical incision in addition to lateral bank erosion. So Protocol 1 only focuses on erosion potential of lateral bank erosion potential. Protocol 5 incorporates the vertical component. So in order to do this, you should compare future or equilibrium conditions to existing conditions. So the equilibrium condition represents what a channel would look like if the channel was left alone and continued to incise until the equilibrium slope and the banks continued to erode to the stable angle of repose. So equilibrium conditions are not the design conditions and really just represent what the channel would look like if the existing instabilities were not addressed. So Protocol 5 is the method to determine the volume of sediment that would have to erode in order to meet these conditions. It does assume that channel planform remains the same, so there aren't going to be any channel avulsions over time. And in order to actually calculate this volume, you can use 3D surface modeling. there are 4 components for Protocol 5 that need to be determined. So the base level control point needs to be determined, and then the equilibrium slope, bottom width, and bank slope have to be calculated. So I'm going to go into a little bit more detail on each of those 4 components. Before getting into the computations for Protocol 5, there is fieldwork requirements to actually run these calculations. So the nutrient and bulk density requirements of Protocol 1 are still applicable. You should collect a minimum of 3 surveyed cross sections, determine the bed material and conduct a pebble count. And you should also note any locations of significant changes in typical bed material, because if the bed material changes between a fine sand bed to a coarser material, a different equilibrium slope equation may become applicable. So I'll show each of the equilibrium slope equations, which hopefully that'll make a little bit more sense. You should also take note of any infrastructure or bedrock within the channel that's not subject to erode. And then having profile data helps indicate the existing slopes. So the first step for Protocol 5 is determining the base level control points. So the control points define the maximum extent of vertical degradation at a project without intervention. So examples of control points may be if there's bedrock within the channel, there's a confluence with another channel that's stable. The channel itself might reach its own equilibrium condition. So if it's within 5% of a calculated equilibrium condition, or there might be infrastructure that's preventing any further erosion. You would start with the downstream control point and then do your upstream control point. So for your downstream control point, you may have situations where you have more than one control point per project length. In this case, there are 2 downstream control points. The most downstream represents the end of the restoration, and the second is at the upstream extent of the bedrock that's in the middle of the project. So the bedrock is acting as a grade control and is not subject to erode. After determining your downstream control point, the next step is determining your upstream control point. So the upstream point defines where the erosion potential ends. If there's no defining point at the upstream extent of restoration, like a pipe outfall, the upstream limit is defined by this particular equation. You would need to traverse the existing alignment upstream of the beginning of restoration for the length you need to check, basically to ensure that there's no other control point that would be acting as a grade control. So after determining the upstream and downstream control points that denote the length of the stream that's subject to erode, the next step is determining what the stable equilibrium slope would be between those 2 points. So the equilibrium slope equations are dependent on the typical bed material. So there's one specific equation for cohesive beds, a different equation for sand and fine gravel, and then there are 4 separate equations for beds that are coarser than sand. The results of those 4 equations would be averaged, and you'd get one calculated equilibrium slope. The inputs required for these equations, along with the equation used in sand and fine gravel bed conditions, requires inputs that are based on specified flows. So the lower the flow used, the higher the resulting slope will be, which will result in the smaller amount of erosion potential. So this length is really where you can find each of the individual equations, as well as the required input parameters for each of them. So after determining the equilibrium slope the equilibrium bank slope has to be determined along with the equilibrium bottom width. So there is a default value for the equilibrium bank slope, which is 1.76 to 1. And then in order to determine the equilibrium bottom width, you would average 3 existing conditions cross sections. So that does assume that your equilibrium bottom width is going to be identical to your existing conditions bottom width. So after determining the control points, equilibrium slope, equilibrium bank angle, and bottom width, the next step is determining the volume of sediment that would be eroding in order to reach these conditions. So you would have to calculate the difference in volume between existing condition surfaces and an equilibrium surface. So just to reiterate, the equilibrium condition represents what the channel would look like if the channel was left alone and continued to incise to the equilibrium slope, and the banks continued to erode to the stable angle of repose. So an equilibrium surface is generated by projecting the equilibrium slope, bottom width, and bank angle upstream along the existing alignment, starting at the downstream control point and ending at the upstream control point. So the most accurate way to determine this volume is by using a 3D program, so Civil 3D or En-ROADS, but you can use the average end area method to do more of a cross-section analysis to determine volumes. So the result of comparison of the existing conditions to equilibrium conditions will result in a total volume of sediment. It's assumed that it would take a stream 30 years to actually reach these conditions, which is why the total volume that's calculated has to be divided by 30, and that would result in an annual prevented sediment per. And then you would apply a 50% efficiency, just like you did to Protocol 1, which is assuming that the proposed restoration will really be 50% effective at reducing the erosion. Same as the computations in Protocol 1, we estimate the volume of prevented erosion, then multiply by, or then determine how much total spended sediment, total nitrogen, and total phosphorus there is by multiplying the volume by bulk density and nutrient concentrations. So I'm going to step through an example of Protocol 5. This is a short, steep restoration project in Baltimore County. There were high existing slopes greater than 7% and existing head cuts within the channel. It qualified for Protocol 1 and Protocol 5, but you cannot claim credit for Protocol 1 and Protocol 5 on the same reach. So for a given project, there may be portions of a restoration that qualify for Protocol 5 and other portions that qualify for Protocol 1. So you may have Protocol 1 and 5 applied to the same project, but the reach that they're applied to cannot overlap. So Protocol 5 typically results in higher reductions than Protocol 1. So Protocol 5 was calculated for this project. So the first step is to determine the upstream and downstream control points. So the downstream control point was at the end of restoration and was a culvert, and the upstream control point was at the beginning of restoration and also was a culvert. So there was no bedrock or infrastructure between the control points, so there were only these two defining points. Equilibrium slope was determined from the 4 equations specific for beds coarser than sand. The input values were based on a design discharge of a 1 1/4 year flow, which results in less sediment erosion potential. The average of the 4 equations resulted in an equilibrium slope of 0.8%. And there was the default bank angle of 1.76 was utilized, and the average bottom width was 3.1. So the average end area method was used, and cross sections were compared to determine the potential volume. So the total volume was determined, and then it was annualized by dividing by 30, and the 50% efficiency was applied. That was then multiplied by the site-specific bulk density to result in a total suspended sediment reduction and that was 125.8 tons per year. Then you would determine your total nitrogen and total phosphorus reductions by multiplying by site-specific nitrogen and phosphorus concentrations. In this case, this project was constructed in the fall of 2019, and assessments were completed between 2016 and 2018 before sampling guidance was available. So the previous default values of 2.28 for total nitrogen and 1.05 for total phosphorus were used here, but those values really cannot be used anymore. So in the end, you have the total nitrogen and total phosphorus concentrations calculated. So at this point, I'm going to pass it back to Shannon, and she's going to talk a little bit more about Protocol 2 and 3.
Thanks, Hannah. So for protocols 1 and 5, we've been talking about credit that's based on preventing sediment from channel erosion. Protocols 2 and 3 are looking at denitrification and sediment capturing processes that the restored channel can perform. The protocol 2, the effective hyporeic zone, is looking at the denitrification processes during base flow and provides only nitrogen load reduction credits. Protocol 3 is looking at the benefits during overbank flow and looks at two major schools. One is the legacy sediment removal, where you're lowering the floodplain to reconnect the channel, and the other would be raising the stream bed. So again, these take effect next summer, and this guidance was just recently finalized in late October of this year. These also have armoring limitations similar to those that Hannah discussed earlier. And these also provide credits for the difference between the pre and post restoration condition for nitrogen reduction. Talk more about Protocol 2. The effective hyporeic zone is defined as the lateral extent where the restored floodplain elevations are less than 18 inches above the low flow water elevation. So this represents the typical root zone that facilitates hyporeic exchange and provides a carbon source for denitrification. To qualify, your restored reach must maintain or improve base flow conditions. The new guidance defines a base denitrification rate and then requires that site adjustment discounts are applied. The new guidance eliminates the criteria requiring the bank height ratio to be less than or equal to 1. It cautions to avoid extended ponding and inundation in the floodplain, and also provides guidance for on-site soil and groundwater testing. The basic steps to computing credit through Protocol 2 involve first defining the area of the effective hyporeic zone, and then applying the base denitrification rate to that area, and then finally applying the site-specific discount factors. So the base flow reduction factor is applied, for example, if the stream only has seasonal base flow or only flows during runoff events. The floodplain height factor looks at the restored floodplain height above the stream bed riffle elevations or low flow water surface elevations, and then reductions are applied if the height is more than 0.75 feet. The last reduction factor is the aquifer conductivity, which looks at the dominant materials within the stream bed and below the floodplain soil of the effective hyporeic zone. The cobbly gravel, gravel, sand, and peat materials get full credit, with silty clay getting the least amount of credit. So now we'll walk through a simple example. We have a single threaded meandering channel with perennial base flow. The post-restoration floodplain surface is 0.67 feet above the low flow water surface elevation level. The approximate floodplain width is 100 feet or 50 feet on either side. The channel width is 10 feet. The post-restoration soil type is a silt loam, and the length of restoration is 3,740 feet. So the first step is to calculate the extent of the effective hyporeic zone. And in our example, we'll define the, multiply the floodplain width times the length of restoration, and then the channel width times the length of restoration. The example in the guidance keeps the floodplain and channel computations separate throughout the process, and then adds the resulting load reductions together at the end. So the next step is to multiply the base denitrification rate by the effective hyporeic zone for each the floodplain and the channel. And that step results in a total reduction of nitrates per year of 1,107. But then we'll need to apply our specific discount factors in step 3. So similar to the example that's provided in the guidance, our example, there are no discounts applicable for the base flow condition or for the floodplain height. However, because the soils are dominated by silt loam, the aquifer conductivity reduction factor of 0.4 is applied to the floodplain. This example results in 503 nitrates per year removal, which is reported as total nitrogen per year. If pre-restoration conditions include wetlands or existing areas within 18 inches of the low flow water surface elevation level, the pre and post conditions should be computed and credits are only earned for the difference. So we're not going to get into the details for Protocol 3, but we have identified some of the major updates in the recent guidance that came out in late October. Again, Protocol 3 is looking at nutrient and sediment reductions during overbank flow. Now the guidance is using a downstream method with scaled USGS data to estimate annual volume of stream runoff diverted into the floodplain and eliminates the upstream watershed to floodplain surface area ratio requirement. HEC-RAS modeling is used for this protocol to determine the area where the floodplain water surface elevations are less than 1 foot maximum depth, or the guidance also allows for this area to be computed based on the floodplain velocities, where the velocities are less than 2 feet per second, up to a 3 foot water depth, or the 10-year water surface elevation, whichever is lower. The guidance also specifies that a Manning's roughness coefficient in the floodplain of 0.07 and in the stream channel of 0.035 should be used. There is a non-tidal wetland expert panel protocol such that if you have wetlands or if you have wetlands in your floodplain and are using this non-tidal wetland protocol to compute credits, you cannot also take credits via Protocol 3 for those same areas. So there's no double dipping there. The guidance also spells out some unintended environmental consequences that need to be evaluated and addressed during the design phase. So in summary, the Bay protocols provide a method to compute sediment and nutrient load reductions for stream restoration, allowing projects that meet the established criteria to get credit toward Bay TMDL, local TMDLs, and MS4 permit requirements. The new protocol guidelines discussed take effect next summer in July of 2021. There is a lot of additional information and detail in the guidance, so please refer to them before performing these computations. There's also opportunities for nutrient and sediment load trading in Maryland and in other states, so we encourage you to look into those opportunities as well. So now we've talked a lot about nutrient and sediment load computations. Now we're going to talk about impervious credits, impervious acre crediting. So in Maryland, MS4 permits are issued in 5-year permit cycles, and in Maryland, they use water quality treatment of untreated impervious surfaces to track progress toward the Bay TMDL. MDE just began reissuing draft permits, which will again require treatment of 20% of the untreated impervious areas. Stream restoration is allowed as an alternative best management practice, or BMP, to get equivalent impervious acre credits. In 2014, the MDE guidance for impervious acre crediting for stream restoration allowed for 1 acre of credit for every 100 linear feet of restoration. In April of 2019, the guidance was revised and allowed up to a 3-fold increase for that credit. So for 100 linear feet of restoration, you could earn, say, 3 acres of impervious acre credits. Next slide, please. So in June of 2020, there was again revised guidance from MDE for determining equivalent impervious acre credits for stream restoration and other BMPs for restoration projects being applied to the next MS4 permit cycles. I'm now going to kick things back to Hannah, and she's going to walk through the new guidance and provide example computations for the impervious acre crediting.
Thanks, Shannon. So for stream restoration, impervious acre credits, credits have to be calculated by converting the nutrient loads calculated from the protocols to impervious acre credit. So in order to do this, you need the difference between loadings from forest and impervious land cover. The pollutant loads are estimated annual loads from either the combined impervious road and impervious non-road land covers or the statewide average forest cover. The delta values represent the difference between true forest and aggregate impervious loads to signify the maximum restoration potential. So in the 2020 guidance, there are revised pollutant loads for impervious and forest land cover. There's also no longer a drainage area cap on impervious acres. And outfalls really are not creditable unless protocols are applied because you cannot use the planning rate for credit. So to determine the equivalent impervious acres, the reductions from all of the protocols, so protocols 1 or 5, 2 and 3, are summed together for sediment, nitrogen, and phosphorus individually. Each of those values is then divided by its respective delta value that's provided by MDE. And then those values are averaged to result in equivalent acres. So here are the revised unit loads and then the resulting revised delta values. So your total suspended sediment reduction, total nitrogen reduction, total phosphorus reduction from your protocols is divided by its respective delta and then divided by 3 to average it to result in equivalent impervious area credit. So just to look back at the Protocol 1 and Protocol 5 examples, the Protocol 1 project was about 200 linear feet and the equivalent impervious area was 3.98. So that's pretty close to the planning rate of 0.02 acres per linear foot. The Protocol 5 example was also a short project, about 300 feet, but the calculated equivalent impervious acre credit was 35.4 acres. So this really is a 10-fold increase in credits compared to the 2014 guidance where this project would have only received 3 credits. I wanted to touch a little bit on delivery factors. So the previous Protocol 1 guidance required an application of a sediment delivery factor that was specific to physiographic region. So the delivery factors are removed from the protocol computations entirely now. Instead, delivery factors that are unique to each land river segment are applied to your local TMDL reductions to generate the reductions that represent the Bay TMDL reduction. So depending on how the data is modeled determines if delivery factors need to be applied to the reductions. And just to calculate the delivery factors, you would identify what land river segment the project is located within, download the cast source data to determine the stream to river and river to bay factors that are specific to the land river segment. And then you would multiply the 2 factors together to result in each individual delivery factor. And the guidance for really calculating the delivery factors is included as an appendix to the protocol guidance.
Thanks, Hannah. So as we mentioned, many streams are impaired due to excess nutrients. So perhaps even if you live outside the Chesapeake Bay watershed, these methods might be used to address your local TMDLs and MS4 permit requirements or methods similar to this. Within the Chesapeake Bay, there have been significant updates to the Bay TMDL protocols that have integrated new research and findings. We've seen over the years how the changes in crediting guidelines can have huge influences on our industry and stream restoration projects. More monitoring and research is always needed to continue to learn and improve. We haven't figured everything out just yet. There are also a lot of states, as I mentioned, that allow for sediment and nutrient credit trading, which is another opportunity to incentivize stream restoration. The next slide, I believe, has some of the links that we've shared today. And again, those will be emailed out to everybody who's attended today, so that you can, at your convenience, go through and use these resources at on your own time.